Welcome to part 2 of this week's online lecture. In part 2 we will discuss reducible representations. So we have seen how we can determine the symmetries of mathematical functions. To determine the symmetries of vibrations, we simply need to determine the symmetries of the mathematical functions that describe them. However, what are these mathematical functions? Well, to a certain extent we do not have to worry. Group theory can be used to determine them at the same time as determining their symmetries. If we consider water once again, we know that it has 3 vibrations. We therefore need as a minimum 3 coordinates to describe these vibrations. Cartesian coordinates on each atom would involve 9 coordinates, and would seem to add a great deal more complexity than is needed. In many cases, it can make sense to use what are known as internal coordinates. In the case of water, we can use the 2 bond lengths and the bond angle to describe the vibrations of the molecule. In fact, it is better to use the displacement from equilibrium. So we can have a displacement of bond 1 away from equilibrium, that is delta 1 is equal to R1 minus RE, and a displacement of bond 2 away from equilibrium, that is delta 2 is equal to R2 minus RE. Similarly, we can have a displacement of the bond angle away from equilibrium, that is delta theta is equal to theta minus theta e. So with these displacements defined, let us look at the effect of the symmetry operations on these displacements. The effect of the symmetry operations on the displacement on atom 1, that is delta 1, is given in the diagram at the top of the page. The identity symmetry operation leaves the displacement unchanged. C2 moves the displacement onto atom 2. Sigma xz also moves the displacement onto atom 2, whereas sigma yz leaves the displacement unchanged. We can also determine the effect of the symmetry operations on delta 2 and delta theta. The effect of the symmetry operations on delta 2 is analogous to that on delta 1. That is, the identity E and sigma yz operations leave the displacement unchanged, whereas C2 and sigma xz moves the displacement onto atom 1. Delta 2 is transformed into delta 1. For delta theta, the symmetry operations leave the displacement unchanged. This means that delta theta has the symmetry A1 because it is totally symmetric with respect to the symmetry operations of the point group. For delta 1 and delta 2, the coordinates are interchanged by some of the symmetry operations. Because of this, we must consider these coordinates together, and we cannot consider them separately. To describe what is going on, we need to use matrices. But don't panic. The reason I show the matrices is to show formally how to determine the character of the symmetry operation for a particular representation. As you will see shortly, there is a shortcut, which will mean that you will never have to identify the matrices themselves. We can operate on the vector of coordinates delta 1 and delta 2 with each of the symmetry operations. For instance, the identity leaves the vector delta 1 delta 2 unchanged. This can be written as the product of the vector delta 1 delta 2 with a 2 by 2 matrix, a transformation matrix. The character of the representation under the identity operator is thus the sum of the diagonal elements of this matrix. So 1 plus 1 is equal to 2. Thus the character is equal to 2. The same can be done for the C2 operator. The C2 operator operates on the vector delta 1 delta 2 and transforms delta 1 into delta 2 and delta 2 into delta 1. This can also be written as the product of the vector delta 1 delta 2 with a 2 by 2 transformation matrix. The character of the representation under the C2 operator is thus the sum of the diagonal elements of the matrix. In this case, the diagonal elements are 0 and 0, and so the character is 0. To review, what we are trying to do is to determine what is known as the representation of the displacements delta 1 and delta 2. Delta 1 and delta 2 are the basis functions we are using to describe vibrations. The reason for doing this will become clear soon. We noted that we could not treat them separately because the symmetry operations mixed them. The character is the trace, that is the sum of the diagonal elements of the transformation matrix. However, note that we get a +1 contribution to the character for each basis function, that is delta 1 and delta 2, that is left unchanged, and we add 0 for each basis function that gets turned into a different basis function. We would get -1 if there was a change of sign, that is a 180-degree change in direction of the basis function. Following this shortcut procedure, we get the following representation for our basis set delta 1 and delta 2, that is 2, 0, 0, 2. Note that under the identity, both delta 1 and delta 2 are unchanged and so contribute both +1 to the character under the identity. But note that under the C2 operation, both delta 1 and delta 2 move, and so therefore contribute 0 to the character under C2. This is the same for the sigma v xz symmetry operation. Whereas under the sigma v yz symmetry operation, both displacements delta 1 and delta 2 are unchanged, and both therefore contribute +1 to the character under sigma v yz. This representation 2, 0, 0, 2 does not correspond to any of the irreducible representations, that is, the symmetry species A1, A2, B1 or B2 in the character table for the C2V point group. However, note that the representation 2, 0, 0, 2 can be found by summing A1 with B2. Remember that A1 has the representation 1, 1, 1, 1, and B2 has the representation 1, -1, -1, 1. So 1 + 1 is equal to 2 under the identity, 1 + -1 is equal to 0 under the C2 symmetry operation, 1 + -1 is equal to 0 under the sigma v xz symmetry operation, and 1 + 1 is equal to 2 under the sigma v yz symmetry operation. This means that our representation for the basis set delta 1, delta 2 is a reducible representation which is equal to A1 plus B2. We did this by inspection, but we need a more general way of doing this. The reduction formula provides this general method. But note, however, that if you are able to reduce the representation by inspection, then you do not need to use the reduction formula. There is only one possible set of irreducible representations for any reducible representation. If you do the reduction by inspection, you will have solved the reduction problem. The reduction formula is used to determine the irreducible components of a reducible representation with character chi r. The reducible representation gamma occurs n sub gamma times, where n sub gamma in this formula is equal to 1 over h times the sum of all the symmetry elements R of the product of the character of the irreducible representation gamma under the symmetry operation R and the character of the reducible representation under the symmetry operation R. H is the number of symmetry elements in the group. The C2V point group has 4 symmetry elements. It is easiest to see what is going on by doing an example. Let's apply the reduction formula to our representation 2, 0, 0, 2. The number of irreducible representations with A1 symmetry is computed in the top row. It is equal to 1/4, which is the 1 over h factor, times the sum of 1, which is the character of the A1 under the identity, times 2, which is the character of our representation under the identity, plus 1, which is the character of A1 for C2, times 0, which is our character of our representation under C2, plus 1, which is the character of A1 for sigma xz, times 0, which is the character of our representation under sigma xz, plus 1, which is the character of A1 for sigma yz, times 2, which is the character of our representation under sigma yz. This sums to 1/4 of 2 plus 0 plus 0 plus 2, which sums to 1. This process is repeated for all the irreducible representations of the point group. Note that this process reveals that our representation for the basis set delta 1, delta 2 is composed of two irreducible representations, that is A1 and B2. This is exactly the result we identified by inspection. But how should we interpret this result? The interpretation of this result is that we can construct a linear combination of the two quantities delta 1 and delta 2 that has A1 symmetry and another combination that has B2 symmetry. Fortunately, there is a standard formula for this. To get a function of symmetry gamma, we start with either delta 1 or delta 2, it does not matter which, and apply the projector P gamma. P gamma is equal to L sub gamma is over H times the sum over all the symmetry elements R of the product of the character of the irreducible representation gamma under the symmetry operation R and the symmetry operation R. L sub gamma is the dimension of the irreducible representation gamma and is equal to the character of the identity for that irreducible representation. Once again, it is easiest to see what is going on by doing an example. Let's apply the projection formula to our basis delta 1. The projection of symmetry A1 on delta 1 is given in the top row. It is equal to the dimension of gamma, which is equal to 1, over the number of symmetry elements, which is 4, times the sum of 1, which is the character of A1 for the identity, times the identity operator on delta 1, plus 1, which is the character of A1 for C2, times the C2 operator on delta 1, plus 1, which is the character of A1 for sigma xz, times sigma xz on delta 1, plus 1 times the sigma yz operator on delta 1. This is equal to 1/4 times delta 1, that is the result of the symmetry operation on delta 1, plus delta 2, that is the result of the C2 operation on delta 1, plus delta 2, which is the result of the sigma xz operation on delta 1, plus delta 1, which is the result of the sigma yz operation on delta 1. This is all equal to 1/2 times delta 1 plus delta 2. This process is repeated for all the irreducible representations of the point group. Note that this process reveals that there are no linear combinations of our basis set delta 1, delta 2 that transform like A2 or B1. notice that trying to project an A2 symmetry from the basis function delta 1 results in 0. Similarly for B1. This is exactly the result we expected, as those symmetries do not exist in the decomposition of the reducible representation. The projection of the symmetry B2 on delta 1 results in 1/2 of delta 1 minus delta 2. To repeat, the fact that we get 0 when we try to project out a combination of our basis functions with A2 symmetry and a combination of our basis functions with B1 symmetry just means there is no A2 or B1 function that can be found, which we already knew from the reduction formula. As a result of this process, we have a coordinate which we'll label QS, which is equal to 1/2 of delta 1 plus delta 2, and this describes a symmetric stretch. And we also have a coordinate QA, which is equal to 1/2 delta 1 minus delta 2, and this describes the asymmetric stretch. The remaining vibration is the bend Q theta. The symmetric stretch thus looks like this, with delta 1 and delta 2 in phase. The asymmetric stretch looks like this, with delta 1 and delta 2 out of phase, and the bend looks like this. This is the end of part 2 of this week's online lecture. Please continue on to part 3.